All right, so continuing with what we were talking about in the last video, um, we're going to start with a table that's in the book. So this is just a table of derivatives and antiderivatives. You can kind of see the relationship. Um, all the properties that you have with derivatives, such as multiplying by a constant, will apply to the antiderivative. So adding two functions, you can add the derivatives, or going the other way, you can add the antiderivatives. Um, the derivative of a constant times x is just the constant. So the antiderivative of the constant is the constant times x. So we're just going in the opposite direction. Here's the one that we were talking about in the first video, ln of x. E to the x, the derivative of e to the x is e to the x. And so the antiderivative of e to the x would also be e to the x plus constant. And then if we're going to look at the derivative of say 5 e to the 5x, the derivative of that is 5 times e to the x. We take the derivative of the exponent. So likewise, when we do the antiderivative of e to the constant times x, then we are going to get the antiderivative. Well, not the antiderivative, but we're going to divide by that constant. So that now, if we take the derivative of this function, we would get 1 over k e to the kx times the derivative of kx, which is k. So k times 1 over k would make that be a 1 in front. And then the derivative of a to the x is that, and then antiderivative would be dividing by ln of a instead of multiplying by ln of a. So those will be useful to know. Like with most formulas, though, instead of memorizing formulas, it's usually a better idea to use them a lot. And then the more you use them, the less you have to think about memorizing them and just do a rote memorization. So I would suggest you get enough practice to where you know these, not that you're memorizing those and then trying to do problems. Try to do the problems and you'll memorize the formulas as you go. All right, so let's look at another example. And so this one, this is not a polynomial, but we can treat this kind of like a polynomial as far as getting the antiderivative. And I would suggest that we write this. We're going to find all functions g such that the derivative is given here. And so let's rewrite this with exponents. So square root of x would be x to the 1/2, and then we're going to write 4 over x squared is 4x to the -2. And so now we can use the antiderivative power rule, and it should be a lot easier than thinking about what the antiderivative of square root x would be, or x squared. And especially with this one, I would suggest that because you don't want to get, because you have to add 1 to the exponent, so you don't want to add 1 to 2. You got to add 1 to -2. So I would suggest that you write these with the exponent in the numerator, so that then it's easier. So g of x, so this is part A. G of x is going to be, we'll kind of do this in 2 steps. You should get to where you can do this without having to do this step. So we're going to add 1 to the exponent and then divide by the new exponent. We're going to add 1 to the exponent and then divide by the new exponent. And then we're going to have to add a constant. And so this is 6 divided by 3/2. That is going to be 4x to the 3/2. And then -4 divided by -1. So that will be plus 4x to the -1. So -2 plus 1 is -1. That's a 3. And if you like, you could put this as 4 square root x cubed plus 4 over x plus c, or you could probably leave it like this and that would be fine as well. So that's this would be all functions, and you can plug in any real number for c. That would be all functions whose derivative is given here. Now, of the functions in part A, which one satisfies g of 1 equals 5? So here we are going to take this general antiderivative. The x is going to be 1, the y is 5, and we're going to figure out what c is to make the function go through this ordered pair. So set it equal to 5, and we're going to plug in 1 for x. And this is obviously pretty simple. 5 equals 4 plus 4 plus c, which means c is -3. And so then our specific function for that is 4 times the square root of x cubed plus 4 over x minus 3. So whenever you're given a specific ordered pair, there's only going to be one function with that specific derivative that goes through that specific ordered pair. So just plug in the ordered pair for the x and the y, solve for c. No big deal. All right. So then the next one, more antiderivatives. So now we have an exponential function, and we'll call this capital F of t. And we are going to have 6. And if you need to refer back to the formula on the last page, you can do that. But keep the exponential part the same, and then we're going to divide by the derivative of that. So instead of multiplying by the derivative, we are dividing by the derivative. So divide by a -0.3. And then the derivative of 8 is just 8t. So the derivative of a constant is 8 times whatever the input variable is, and then plus c. And so then we can simplify this. 6 divided by -3 is -20. E to the -0.3t plus 8t plus c. And again, you can do this with any of your antiderivatives. You can take the derivative of your antiderivative, and you should end up with the original function. So it's always a good idea to check yourself, especially when you're learning these, even after that, because it's easy to make arithmetic mistakes or simple algebra mistakes. In fact, I would say as many algebra mistakes are made in this class as there are calculus mistakes. So don't get too overconfident in your ability to not make simple mistakes. We all do them, and so it's a good idea to go back and check yourself, especially on tests where it will make a difference. All right, so this one, let's rewrite this with p. Actually, we don't need to do that, because when it's 2.9 over p or 2.9 over x, antiderivative is just going to be the ln function. So let's add 1. Add 1 to that exponent, and then divide by the new exponent. And then this will be 2.9 ln of absolute value, can't forget that, plus c. And so this would be 0.4 divided by 4, which would be 0.1, p to the 4th, and then this one, 2.9, don't really have to change this one, ln of absolute value of p plus c. So there we go. So as you can see, when we just have a string of terms separated by addition or subtraction, we just do the antiderivative term by term, which is what you see on this page. So that's what this is. Well, this line, I guess, is saying if you're adding two functions, the antiderivative is just the term by term antiderivative. All right, so then looking at number 5. Oops, where did we go? All right, there we go. All right, so now we have a definite integral. When you do the definite integral, you don't have to worry about the constant term. And I'll do this, well, we'll do it the way you should do it. And then I'll show you how the constant term does not change anything. So the antiderivative, and we'll just write this and then find the antiderivative. The antiderivative of 1 over t is ln absolute value of t. And then we don't have to do the constant. So what we're going to do is we're going to evaluate this this antiderivative at the limits of integration. So using the fundamental theorem of calculus, we're going to evaluate the function at the upper limit minus the value of the function at the lower limit. And of course, you don't need the absolute value here, but go ahead and leave them in. Ln of 3 and then ln of 1 is just 0. So answer is ln of 3. Now, if you do add in the constant, what would that do? So let's just look at this real quick. If you do add in the constant, it won't matter. The constant does not do anything to help you at all. So antiderivative plus c, evaluate at the limits, and we have ln of 3. Now, if you evaluate c when x is 3, it's just going to be c. And then we're going to subtract when we evaluate at 1. So ln of 1, and then evaluate c when x is 1, it's just going to be c again. No, plus c. And so what you notice is the c's will just cancel out. So those will never make any difference when we're doing a definite derivative, which is what this is called. So when you have limits of integration, it's called a definite integral, which we defined in the last section. All right, maybe one or two more for this one. Find the area under the curve y equals e to the x. And so all that is doing is finding the integral from 1 to 3 of the function that will give the area under the curve. And so the antiderivative of e to the x is just e to the x. Evaluate it from 1 to 3. So we have e to the third minus e to the first. And you can write that or not write it, just so we're clear what we're doing. All right, very basic. And let's say one more, and then we'll stop this one and start another one. So general indefinite integral or indefinite antiderivative. So the antiderivative of 10x to the fourth, we have 10x add 1 to the exponent, divide by the new exponent. The derivative of e to the x is e to the x. Constant does not matter. We're just going to leave that alone. And then add a c. All right. So, well, I guess we could simplify this. So we have 10 divided by 5. So that would be 2x to the fifth minus 3 e to the x plus c. And then that is the answer. All right, so as you can see, these are fairly basic so far, as long as you know the formula, or at least can work backwards in your head from the derivative to the original function. All right, so we'll do some more on the next video.